Hi there, this is Astrophysics. This is Telescopes Lesson 6, and this one's non-optical telescopes. So many of the most spectacular modern images are in fact composites images taken from a number of regions of the electromagnetic spectrum. So the picture below, the Whirlpool galaxy, is such an example taken by the Hubble Space Telescope. It's of the galaxy taken with ultraviolet and infrared, as well as with visible light. So this is the Crab Nebula. Should have learnt about nebulas at GCSE. Basically big clouds of hydrogen gas where stars are born. We'll do them in much more detail in surveying the stars, which is next topic after telescopes. It's got same nebula looked at in radio, infrared, visible, UV, X-ray using the Chandra telescope, and then high energy X-ray as well. Right, so single dish radio telescopes. So these consist of a large parabolic dish with an aerial at the front. So the atmosphere transmits radio waves in the wavelength range of about 1 millimeters to 10 meters. The ones longer than that, they reflect off the ionosphere. So radio waves are used to study strong radio sources such as the Sun, Jupiter, Milky Way, and many other galaxies. The structure of the Milky Way can be studied using radio waves, as these waves are able to travel through gas clouds where visible light cannot. So our knowledge of what is at the centre of our galaxy has been obtained primarily, obviously using mathematics, but also using radio telescopes as well. And it's postulated that we have supermassive black holes at the centre of each galaxy, by which everything rotates around. So a quick comparison of radio and optical telescopes. So both radio and optical telescopes can be ground-based. The resolving power of a radio telescope is much lower than that of a comparably sized optical telescope. So in order to achieve reasonable resolution, radio telescopes have to use large collecting dishes. So radio telescopes have actually got a lower resolution, a much lower resolution than even the human eye. So the largest radio telescope in the world is the non-stable Arecibo telescope in Puerto Rico, which has a diameter of 305 meters. And the Arecibo telescope was used in the film GoldenEye, final scene, where James Bond fights 006. If you've not seen that film, I know it's old, but it's still pretty good. And there's an image on the top right, a supernova remnant picture taken with light by the Hubble. And then next to it is the same remnant taken with a radio telescope. So, quick question. Calculate the resolving power, or the Rayleigh criterion, of the Jodrell Bank telescope. That's in part of Manchester University. When it's used to receive the 21 centimeter wavelength radio waves given off by the interstellar hydrogen gas. The steerable dish has a diameter of 76 meters. So if you want to do that calculation now, let's have a look then. So the Rayleigh criterion, angle is approximately equal to the wavelength divided by the diameter. So you've got 21 centimeters divided by 76 meters. Obviously the units need to be the same, so if you convert it to meters, that gives us approximately 0.028 radians or 0.2 degrees, which is about 100 times worse than the human eye. Radio telescopes do have high collecting powers. Remember that collecting power is directly proportional to d squared. So obviously these are very large diameter, so they've got a very high collecting power. So let's look at infrared telescopes. So they consist of large concave reflector which focuses infrared radiation onto a detector. Planets and dust clouds in space, while not hot enough to emit light, do emit infrared radiation. So again, that image from earlier, we've got a supernova remnant taken with the Hubble, which we've already seen, and that's the same one taken with the Spitzer IR telescope. Recently launched, 2009, Herschel Space Telescope will, amongst other tasks, be trying to detect the formation of young stars within gas nebula. So like optical telescopes, infrared telescopes can be ground-based. The principal limitation of infrared sensitivity is water vapour in the Earth's atmosphere. So obviously water vapour absorbs a significant amount of infrared radiation. So for that reason, infrared telescopes are built in very dry places at very high altitude, above the vast majority of water vapour in the atmosphere. So suitable locations on Earth include Mauna Kea Observatory, which is incredibly high, 4,205 metres above sea level, and regions of high altitude ice deserts such as in the Antarctica, which is the South Pole. So they need to have detectors shielded from heat, and they're chilled with liquid nitrogen in order to actually form images. So this limits the lifetime of space-based infrared telescopes. For example, Spitzer telescope, launched in 2003, actually ran out of helium coolant in 2009. And the resolving power, or the Rayleigh criterion, of an infrared telescope is lower than that of a comparably sized optical telescope due to the longer wavelength. So Rayleigh criterion is wavelength divided by diameter. And the infrared wavelengths are obviously longer than visible light, so it affects the resolving power in a negative fashion. Right, let's look at ultraviolet telescopes. So this is a galaxy, combined optical and UV image, galaxy M82. The UV is the blue region. So ultraviolet telescopes must be carried by satellites because UV radiation is obviously absorbed by the Earth's atmosphere. Obviously some of it gets through still, you know, UVA, UVB, which can be damaging to health, but fortunately the atmosphere absorbs the vast majority. So as glass absorbs UV, we must use mirrors to focus UV radiation onto a UV detector. And UV radiation is emitted by very hot objects such as stars, supernova, quasars, which we'll do at a later date, and some gas clouds. Resolving power of the Rayleigh criterion of a UV telescope is higher than that of a comparably sized optical telescope, and that's because the wavelength of ultraviolet is obviously shorter than visible light. Alright, moving on. So X-ray telescopes, again, must be carried by satellites because X-rays of very high energy are absorbed by the Earth's atmosphere. So they work by reflecting X-rays of highly polished metal plates at grazing incidence onto a suitable detector. X-rays are emitted by pulsars and the gas around suspected black holes. So we'll do more about pulsars and black holes in subsequent lessons. But a black hole has something called an event horizon around it, which is where the speed of light is equal to the escape velocity. And yet obviously there'll be enormous forces acting in that area, which are called tidal forces. And what they'll do is they'll cause nearby matter to heat up to millions of degrees and subsequently emit different types of electromagnetic radiation, including X-rays. So if X-rays diffraction is insignificant, remember for suitable diffraction, the aperture size has to be comparable to the wavelength. Image resolution is determined by the pixel separation in the detector. So again, back to the supernova that we looked at earlier. So we've got the same supernova remnant taken with the Chandra, which is the low energy X-ray telescope. Next one, gamma ray telescopes. This must be carried by satellites because again, gamma rays are absorbed by the Earth's atmosphere. So we had UV, X-ray and gamma, which must be telescopes that we put in space. So gamma ray telescopes work by detecting gamma photons as they pass through a detector containing layers of pixels, triggering a signal in each pixel it passes through. The direction of each incident gamma photon can be determined from the signals. So some of the most distant objects observed give off bursts of gamma rays, known as GRBs or gamma ray bursts. So gamma ray spur there. Gamma ray burst, sorry. So that's an artist's illustration. Explosion beaming two narrow, oppositely directed jets. You do not want to get hit by a gamma ray burst. If the Earth was hit by a gamma ray burst, all kinds of terrible things could happen, including the atmosphere being ripped away, obviously. Yeah, that wouldn't be good. So with gamma rays, diffraction is insignificant. Image resolution is determined by the pixel separation in the detector. Anyway, that's a decent overview for you. Thanks for watching, and next we'll move on to surveying the stars, and then finally we'll deal with the cosmology section. So thanks for watching.